This review is on 2 sample tests and intervals. I'm going to start out with the review sheet that I made for you guys for difference of test and intervals. And then if you'll notice across the top, it's the difference of proportions and the difference of means, but then it also has matched pairs, which again, remember, is 1 sample, but I put it on here to make sure that you can see the difference between the two. So again, matched pairs is still 1 sample. So the type of procedure is just going to be a 2 sample z-test for difference of proportions or the difference of means. You have to define 2 parameters, a p sub 1 and a p sub 2. If you have males and females, you can do p sub m and p sub f if you wanted to. Same thing for means. Remember, when you do matched pairs, it's mu sub d. So you don't have 2 separate parameters. You go ahead and subtract your 2 sets of data and get the average of that 1 set of data, and that's your mu sub d. I remember on that test, a lot of us forgot our d. Conditions, it's the same old, same old. It has to be random, independent. Because you have 2 samples, you have to show n sub 1 and n sub 2 for both proportions and means. And again, remember, when it's matched pairs, you only have 1 sample, so you only have 1 of those. And then that's unless this is an experiment, and then you would write independence is not needed because it's an experiment. Large counts conditions for proportions. Just be very particular about whether your P's and Q's have hats on them or not. If it is sample data, which most of the time it is, then your P's and Q's need hats on them. If for some reason you're doing a problem and you have population data, then you don't put hats on your P's and Q's. So you need both those to be bigger than 10. And for means, independence is the same, and your normalcy comes from your central limit theorem if both of your sample sizes are bigger than 30. If not, you have to graph them. So you would do 2 box and whiskers and look for strong skewness and outliers. Your null and your alternate, your null is always that there's no difference. So your null is that they are equal. Your alternate, and this is no hats and no x bars. These are p's and mu's because your null and your alternate is always about your population. So p1 equals p2 or mu1 equals mu2. On your matched pairs is that your mu sub d equals 0, so that there is no difference. Your alternates is either that the first one's bigger than the second one, the first one's smaller than the second one, or just that they are different. And this is your right-tailed and your left-tailed and your two-tailed. And then you're always going to set your alpha. If they don't give you one, you're going to let it be 5%. Okay, and then once you clear all your conditions and you set your null and your alternate, you sort of hit this, what we've called a speed bump. When you get there, you look to your formula sheet. You're doing a test. So you need your test statistic. This formula is on your formula sheet. So this is your, but it's the difference of your statistics. So it's p hat 1 minus p hat 2 minus p1 minus p2. And this part right here is always going to equal 0 because you're stating originally that they are the same. But you still write that in your formula. Then you get your standard deviation. Okay. You're pooled because you're doing a test for proportions. So remember, we pictured ourselves a big P for proportions taking a swimming test. That's when you pool it. It has to be pooled. And that's just when you do the top of your P1 plus P2 over your sample sizes. And that's the only time you pool. You don't pool for intervals. You only pool for tests. And you only pool on 2 samples. For means, and this is on your formula sheet. And I think pooled is on your formula sheet. But you just got to know when to use it. And then for matched pairs, this is just x bar sub d. So the difference in your averages of your statistics, that's going to be 0 because again that was your null. And then that's going to be on your formula sheet also. So the standard deviation of the differences over the square root of that one sample size. So now that you have your Z or your T, that's your test statistic, you're going to draw your curve and you're going to find the area. So if your Z is positive, you're going to be over here, and you're going to do your Z to infinity and then 0 and 1. If your Z is over here, you're going to do negative infinity to your negative Z, 0, 1. And if you're two-tailed, you're just going to, whichever one this gives you, positive or negative, you're going to figure out what that area is, but then don't forget to double it. And that's a really, really common mistake and not something you want to lose a point for. TCDF, when you draw it so that they can tell that you know that it has thicker tails. And feel free to write a note out to the side, thicker tails, because it's a T distribution. You've got your lower and your upper and your degrees of freedom. Please write out the formula for degrees of freedom. You've got two samples. Most of the time they're the same, but sometimes they're not. Always pick the smallest one and subtract 1 from it. And then don't forget to double it if you're two-tailed. And then for matched pairs, your degrees of freedom is just n minus 1 because you only have one sample. And then your conclusion, since our p-value is greater than or less than the level of significance for this test, we either fail to reject or we reject H sub O. There either is or is not enough convincing evidence to conclude that. And remember, this conclusion is always your alternate. So if you reject, then there is enough evidence to conclude that H sub A is true. If you fail to reject, then there is not enough convincing evidence to conclude H sub A is true. And then your data is or is not statistically significant based on whether it made you change your mind or not. This is the difference for intervals. Everything is the same. And these shouldn't say tests. These should say intervals. The parameters are the same. The conditions are exactly the same. Then once you do your conditions, this is that speed bump. So a lot of times we go down here to the formula and we get our interval formula off the formula sheet. And then once you get to where you need him, you go back here and find your critical value. So I want to be 95% confident. So if I want to be 95% confident, then I know that there's 0.025 area under that little wing. So I'm going to do 0.025, 0, 1, and get my Z star. Remember, it's plus or minus because it's on either side of the 95%. So that's what's going to go there. Remember, these have hats on them because this is statistic. This is not pooled because we are an interval, and we don't pull on intervals. We only pull on tests. Same thing for means. You're just going to inverse T instead of inverse norm because your means and these are T's. Formula in words is the same, but you're switching to X bars and you have a T star. And so you're going to inverse T percent to the left in degrees of freedom and make sure you include that. Remember, it's the smallest n minus 1. And then that's on your formula sheet as well. Just practice when you're doing these in the notes with me, and then also when you're working on your homework, practice the typing in it on your calculator. Don't assume that you know how to do it and just skip to the answer. Make sure that you're comfortable typing this stuff in. That's not how you want to lose points. We are blank 95% confident that our interval from here to here captures the true proportion or the true mean difference of all difference of men who take this drug versus women who take this drug. Just make sure that your sentence makes sense. Okay, so we're going to do walk through a couple examples just to sort of kind of get you back in the swing of it. I'm going to do this quickly. Feel free to slow it down or go back and watch it again. But these are all problems we've done before, and again, this is a review. So I'm gonna cruise on through this. All right, different varieties of tropical flower are fertilized by different species of hummingbirds. Researchers believe that over time the lengths of the flower and the forms of the hummingbirds' beaks have to evolve to match each other. Here's data on the lengths in millimeters for random samples of two color varieties of the same species of flower on the island of Dominica. So we have this red flower and we have this yellow flower, and these are the lengths of these flowers. It says construct and interpret a 95% confidence interval for the difference in the mean lengths of these two varieties of flowers. So I hope it's super obvious that we have two samples. So we're definitely doing a difference of two, and we're doing a confidence interval. That's pretty obvious. And then it's got a follow-up question that says, does the interval support the researcher's belief that the two flower varieties have different average lengths? Explain. Okay. So we are two sample t interval because these are means for the difference of means. This is an observation, not an experiment, because we're not doing anything. We're just measuring what's already there. Then I defined my two variables, the true mean length of all the red ones and the true mean length of all the yellow ones. When it's the actual AP exam, make sure on the island of Dominica, just make sure don't trim any corners. Conditions. Here we go. Random, yes, it said random sample. Independent, write your formulas. 23 was my first sample size, and that's all red flowers. 15 is less than 1/10 of all yellow flowers. Check that off because you're just assuming. Normal CLT does not apply because samples are too small, and I would probably even say, you know, N sub 1 is less than 30 and N sub 2 is less than 30. Don't just say CLT does not apply, and don't just go to your box and whisker. State that CLT does not apply and tell them why, and then go to your box and whisker. Now, stop for a second and make sure you remember how to find a box and whisker. You're going to put your data into L1, L2. You're going to go to stat plot, select your box and whisker. Just make sure you remember how to get all that stuff, which you'll practice on the homework. Okay, then I go formula. So I get that straight off my formula sheet. It's an interval, so I get the interval formula. Statistic is going to be x sub 1 minus x sub 2, and then my t star, and then my standard deviation. So these numbers, they gave me a big old set of data. They didn't tell me the mean. They didn't tell me the standard deviation. So I typed the first ones. I typed red into L1. I typed yellow into L2, and I did a 2 variable stats, and it broke down all the information for L1 and L2. So that's where this came from, and I wrote that here. Again, that's not required, but it's just nice and tidy and labeled correctly with the right letters and bars and sub numbers. And then I can come here. I've already defined my variables, so I don't have to worry about specifying which one comes first because I've got it here, and I define my variables up top. T star, that's when I come over here and find my critical value, 95%. So I'm going to inverse T, 25%, and I'm going to make sure that I write degrees of freedom is smallest n minus 1, so then 15 minus 1 gave me my 14. Make sure you have T star, and what's going to remind you to do that is because in your formula it says critical value. Critical value gets a star. Test statistic does not. And I'm going to always do the minus 1. Well, and then here's this guy. That's just your standard deviation. Super easy, super straightforward. I'm always going to do the minus 1 first because that gives me the first value of my interval, and then the bigger one second. And if I were you, I would pause this video and type this chunk in, at least to make sure you can get one of them before you continue. Once I get my interval, here's my nice little sentence. I'm 95% confident that our interval from here to here captures the true mean difference, and then I put in parentheses just to clarify that I did red minus yellow in millimeters for all these flowers on the island of Dominica. Okay, now part B said, does the interval support the researcher's belief that the two flower varieties have different lengths? Well, our interval is all positive. So that means that when I did red minus yellow, red was bigger all the time. If I had gotten a 0, they would have been the same. And if I had gotten some negative numbers, that means that yellow is bigger sometimes. Since our interval does not contain the value 0 or negatives, our interval does support the researchers' belief that the two flower varieties have different average lengths. Furthermore, since our interval contains all positive values, our interval supports that the red flowers are longer on average. Okay, let's look at another one. A study by the National Athletic Trainers Association surveyed random samples of 1679 high school freshmen and 1366 excuse me, high school seniors in Illinois. Researchers showed that 34 of the freshmen and 24 of the seniors had used steroids. Excuse me. Steroids, which are dangerous, are sometimes used in an attempt to improve athletic performance. Does the data give convincing evidence of a difference in the proportions of all in Illinois high school freshmen and seniors who've used an antibiotic? Okay, so first things first, we're going to label what it is. Does the data give convincing evidence? So that's a test. Okay. So we are a two-sample z-test because we are proportions. Of the difference of proportions that we are an observation because we're just looking at data. P sub 1 is, and remember there are no hats because this is parameter information, the true proportion of all high school freshmen in Illinois who have used antibiotic steroids. And P sub 2, the true proportion of all high school seniors who've used steroids. Okay, so then let's see. Let's go here. Okay, so I start with my null and my alternate. So my null is that there's no difference. And it says, does the data give convincing evidence of a difference? I don't know which way they want me to go, so I'm going two-tailed. Random, it does say that there are random samples. Independent, I have to test both. So there's my sample size. All high school freshmen in Illinois and all high school seniors in Illinois. My large counts condition, this one's a pain in the rear end when you have two samples. And P hat, because this is data from a sample. In Q hat, sub 1s and sub 2s, throw your formulas in here. And don't stop here and do a check mark. Come here before you do your check mark. Show them all the way through. Okay, and then this is sort of my little stats box. I've got my sample size, my P's and my Q's for sample 1 and sample 2. And notice I went 3 decimal places when appropriate. Apparently this one comes out very nice, or rounds with a 0 in the third spot. Now this is a proportion test. A proportion test, so I have to pool it. So here's top number plus top number over sample size plus sample size. And that gives me my pooled, notice it's P hat sub C. And they want to see that. Okay, so once you're done with your conditions, this is when you sort of hit your speed bump. So you go and find your test statistic because you're doing a test. So for these, this is a Z, not a star because it's not critical. The difference of my P hats minus the difference of my P's, and again, this is going to be 0. And I went ahead and just used those instead of using the fractions. That's totally fine. Here's my formula. Notice I don't have sub 1s and sub 2s. I have sub C, but I still have my N sub 1 and my N sub 2. So the tops are the same, but the bottoms are your two different sample sizes. Type this in right here, and I got Z to be 0.543, so now I'm going to use that and figure out what my p-value is. Now remember, we are two-tailed because our alternate hypothesis was that they're just not equal to each other. So that's the positive one, so then I do the negative one, and I went ahead and did 2 times my normal CDF, and I did the positive 1 to infinity, 0, 1, and I've already 2 times it. and that's my p-value. Now that's a big p-value. So since our p-value is greater than the level of significance for this test, and then I put that in parentheses just to further clarify, we fail to reject H sub 0. There's not enough convincing evidence to conclude that there is a difference in the true proportion of all high school freshmen and seniors in Illinois who have used anabolic, I can't say that word, steroids. Our data is not statistically significant. Okay, and the last two examples that we've done, that they would earn you full credit, top points on any free response question. And these are very typical examples of what a free response question is going to look like. Okay. Many students at Matt schools claim they can think more clearly while listening to their favorite kind of music. Matt thinks music interferes with thinking clearly. To test this, he recruits 84 volunteers and randomly assigns them to two groups. The music group listens to their favorite music while playing a Match the Animals memory game. The no music group plays the same game in silence. Below is a dot plot and some descriptive stats for the number of turns it took each subject to complete the game. Okay, now as you're reading this, once you've sort of reviewed experimental design, you should see massive flaws in this experiment. Number one, you should never compare how someone does with music to how someone else does without music. This should have been done as a matched pairs design, but it didn't. But that would be a great free response question. Like, how would you restructure this experiment, correcting some of its faults? Okay, anyway, it has given us a little mini tab. So you can see your sample size is 42 and 42, which is nice because the CLT applies. You've got your two means and your two standard deviations. Does this data provide convincing evidence that listening to music increases the number of turns required to finish the memory game? Suppose Matt allowed people to choose whether or not they were in the group that listened to the music while playing the game. Give an example of a problem that might arise, and interpret the p-value. Oh yeah, remember that one. Interpreting the p-value. Okay, so we're going to start with what this is. This is a test. It's two sample t-test for the difference of means, and this is an experiment because we are imposing a treatment. Mu sub 1, the true mean number of turns it would take. And again, go back and look at what they measured. Below is a dot plot and some descriptive stats for the number of turns it took each subject to complete the game. Okay, so our data is the number of turns with music, and the mu sub 2 is the same thing without. Then I go into my conditions. Random treatment was randomly assigned. Independent, here you go. Not needed, and I would probably write because it's an experiment. Normal, CLT applies since both are greater than 30. Again, put your Captain Obvious hat on and state the obvious. I came in here and did my null and my alternate. My null is that there's no difference between the two mu's, not x bars, mu's. H sub A, let's go back and read the question. Does this data provide convincing evidence that listening to music increases the number of turns it takes to finish the game? So that would make mu sub 1 be greater than mu sub 2. The number of turns with music is bigger than without. And then I just pulled my little stat box from the mini tab. All right, since this is a test, I go find my test statistic. There's the difference of my x bars, the difference of my mu's, my standard deviation, plug your numbers in. This is t, not t star. That gives me this t. And then I take this and come up here and find my p-value. Always draw your curve. This is right-tailed, so a t-CDF from 2.588 to infinity with the degrees of freedom. I think they were both 42. And got my p-value, which is tiny. Always label it. Again, remember, no floating numbers, no naked math. Always label it. Since our p-value is less than the level of significance for this test, we reject H sub O. Our p-value is tiny, so not much stood a chance. There is enough convincing evidence to conclude that the true mean number of turns while listening to music is greater than not listening to music. Again, that's your very clinical sentence. Then here's your, okay, I'm going to make it make sense. Listening to music interferes with thinking clearly. And you could write that sentence a bunch of different ways. But give me a very cold, statsy kind of a sentence, and then do like a you're talking to the public kind of sentence. Our data is statistically significant because it made us change our mind. Question B said, suppose Matt allowed people to choose whether or not they were in the group that listened to music while playing the game. Give an example of a problem that this might arise. So students who are enthusiastic about music would choose the music treatment, and we wouldn't be able to distinguish between the effect of the treatment and their enthusiasm. And then C says, interpret the p-value. Okay, here we go, p-value. If there is no difference, okay, so assuming the null is true, if there is no difference in the true mean number of turns it takes to compute the memory game with or without music, then there is a, and then there's your p-value, probability of getting a difference of by chance alone. Okay, so where's this number coming from? That's the difference of your two X bars. Now, why is it or more? Because your alternate is greater than. So getting a difference of whatever mu sub 1 or x bar sub 1 minus x bar sub 2 is, or greater than, by chance alone. So if there is no difference in the true mean number of turns it takes to complete the memory game, then there is a, whatever your p-value is, probability of getting a difference of, whatever the difference is, or more, by chance alone. Okay, last example. Nicotine patches are often used to help smokers quit. Does giving medicine to fight depression also help? A randomized, double-blind experiment assigned 244 smokers to receive nicotine patches and another 245 to receive both a patch and the antidepressant drug something. After a year, 40 subjects in the nicotine patch group had abstained from smoking, as had 87 in the patch plus drug group. Construct and interpret a 99% confidence interval for the difference in the proportion of smokers who abstain when using the drug and the nicotine patch, and the proportion who abstain when only using the patch. So they're both groups are getting the nicotine patch, but one group is getting the depression drug and one is not. It says right here we're doing a 99% confidence interval. So here we go. Two sample Z interval for the difference of proportions. And it is an experiment because we are imposing a treatment. P sub 1, the true proportion of all smokers like these who used a nicotine patch and abstained from smoking 1 year later. This is not, I didn't get people off the street. This is not random. I had to get people who were smokers. So my population has to have the like these in it, like these people that we specifically used. And then make sure, because this is the proportion, these numbers are on a year later. These are the people who have still stopped smoking a year later. So you have to make sure you say that in your P. Who used a nicotine patch and abstained from smoking 1 year later. These people got the nicotine patch and the drug and abstained from smoking 1 year later. And sometimes we get a little lazy here. Don't do that. See it all the way through. Think about what the numbers represent. Okay, conditions, random, yes, because it was a randomized experiment. We randomly assigned them to the treatments. These people were not randomly picked. Independent does not apply because experiment. LCC, absolutely, easy, straightforward. Okay, then come over here. This is my little stats box. So I've got both my sample size. I've got p hat 1 and p hat 2. And then I declared that I'm going to do p2 minus p1 instead of P1 minus P2, so we should get positive results. Remember, P2 is patch and drug. So I'm hoping that proportion is higher. Well, I don't care, but I'm thinking that that's going to be higher because they got the patch and the drug. So I set it up that way so that I would get positive. You could absolutely set it up this way. That's fine. I just chose to set it up this way, and you can make a little note about why you did it that way. Okay, this is an interval, so I get my interval formula off my formula sheet. This is P2 minus P1 because that's what I chose. Z star because it's a critical value. Nothing's pooled, none of that. Those two numbers, I have to go find my Z. 99%, be careful with your zeros there. So that's 0.5% in each wing. Get my Z star, that's him. And then the first P, or the P2 and Q2 over my sample size for 2. And then my P1 and my Q1 and my sample size for 1, type it in. Then there's my interval. Again, I would pause it, make sure you can type that in and get it correct. So we are 99% confident that our interval from here to here captures the true difference of antidepressant minus no antidepressant. And you could say drug and patch minus patch. In the proportion of all smokers like these who quit smoking for 1 year with the patch and the drug versus the patch alone.